Good afternoon and welcome to Teledyne DALSA's webinar, Our Understanding Line Scan Applications. I'm Maureen Clancy, your moderator and webinar organizer. Our presenter today is Fernando Serra. He's a machine vision specialist with Teledyne DALSA Industrial Products, and Fernando has over 25 years of experience in the machine vision industry. So Fernando, I will take it over to you.
Good afternoon, everyone. We're going to talk today a little bit about line scans and certain ways to apply the technology. So for those that are familiar with vision systems, mostly you're probably familiar with area scan cameras, not line scan cameras. If you're familiar with line scan cameras, some of this information would be a little redundant to yourself. So what makes us decide to go to a line scan solution versus a frame-based camera? Well, the type of product, is the movement of the product, and the use of light. It's hard to do uniform light for a 2D area scan. High-intensity lighting, and also what kind of features or defects are we trying to inspect in the object, and resolution, of course. Line scan cameras have a resolution up to 16,384 pixels today. So the area scan cameras have a sensor with multiple rows of pixels. Usually it's a 4:3 ratio. So you would get a limited on both the horizontal and vertical size, and that's your CCD or CMOS sensor. You capture an image on the CCD and then it's transferred, and it's limited by, of course, your frame time, or the frame rate it's called. Right now, known to commercial cameras, you're limited to a horizontal resolution of 5,344 with data rates up to 760 megahertz. And the part needs to be stationary. When I mean stationary, it could be a moving part, but of course you can strobe or freeze frame that part as it's going by. When you go to line scan technology, line scan sensors have one row of pixels, 2 row of pixels, or the TDIs have up to 256 rows of pixels. The vertical size is not limited because since it's a horizontal limitation by the number of pixels in the row, and we built an image based on movement or in the vertical size. As we capture a line, it gets transferred and the next line gets acquired. So this happens in parallel. As I mentioned before, as of today, we have a camera that can go up to 16,000 pixels with a data rate of 1,179 megahertz. For line scan, you have to either move the part or move the camera. So when is a good time to decide about using a line scan camera? Well, if you need an uninterrupted, image capture. So for example, if you have web material, paper, textiles, metal, glass, fibers, extrusion of metals or extrusion of plastics, free-falling product like molten glass or plastic as well as steel, some postal sorting as well for moving fast envelopes. Also, when you need really, really high resolution, like for example, wafers, flat panels, display, solar cells, printer circuit boards, and then plywood or any kind of medical imaging. And also cylindrical shaped objects, so things that would actually rotate. How do we scan with line scans? Well, the line scan builds a 2D image. What it does is it continues to acquire one line at a time, and generally there's a set of numbers of lines that are set in the frame buffer or in the vision computer that would allow it to say, okay, here's my 2D frame, so the software can analyze that amount of data before the next section of it. There is algorithms that work in the edges of the two frames, so there's no interruption. If you have a defect that happens to be partially in one frame and continues in the other, the vision algorithms work on these kinds of breakage of frames. There are cameras with two line imagers, so instead of having a single row of pixels, there's two rows of pixels. So what it does, it actually takes the image twice. What it allows you to do is allows you to have a brighter image when you have low intensity lighting. Then we have TDI cameras, which stands for time delay integrations. Those cameras can have up to 250 lines or stages. So as you can tell, every time you acquire a line, you're really acquiring 256 times. So this will allow you to reduce the intensity of light. And also, it would allow you to have a much better sensitivity. In today's technology, we also have two interfaces. We used to have something called LPDS that's no longer really used out in the market. But we have GIGI, and also we have camera link base. Those are the data interfaces from the cameras. The gigabit Ethernet, of course, can handle up to 100 megabytes per second. So, for example, our spider tree camera can go up to 74 megabytes per second. Camera link is a parallel bus, and it can handle, or has a specified rate of 600 megabytes per second. And there are some special formats that can handle up to 150 megabytes per second. Camera link have three data configurations or output formats. You have the base, the medium, and the full. Base uses 24-bit data rate, so 255 megabits per second. Single, and that's a single camera cable. Medium uses 48 bits, so twice the bus. So that's 510 megabits per second. So now we use two lines or two cables for the two buses of 24 bits. And the full uses 64 bits, which is again 600 megabytes per second, or two camera cables. There's a new bus called HS-Link. It's actually been pioneered by DALSA, and it utilizes a frame grabber, and it has a specified data rate of 6,000 megabytes per second, theoretically data rate. How do we select a camera for an application? Well, there's a couple of things we need to do. We have to choose the size of the sensor and the speed. To determine the size of the sensor, we have to look at flaws objects in your line or in your product. So a good rule of thumb is make sure that the flaw of the object, it covers at least 3 to 4 pixels. So if we take a look at this example, we're going to have a field of view of 12 inches. And our minimum defect size is 5/1000ths of an inch. So calculate the field of view over the defect size times the minimum number of pixels, which we'll do 3 in this case. And in this example, we got a total of 7,200 pixels. So the next camera closest to the resolution would be 8K camera, or you can split it into two 4K camera with some overlap. To determine the camera line rate needed, we need to figure out the part speed that requires. So let's take the same example, and we use the 12 inches, and we're doing 20 inches per second. Again, this is linear speed, and we're going to be using that 8K camera that we selected before. So let's take the pixel size, so the field of view over the sensor size. So again, 12 inches over 8192, which is the equivalent pixels of an 8K camera. And the minimum line speed will take the 20 inches per second, which is basically 13,654 kilohertz, hertz. So if we use that parameter 8K, 18 kilohertz, that will cover our sensitivity. Or we can use two spider tree 4Ks at 18 kilohertz. Again, we split the image and we do some overlap. How do line scan camera synchronizes to movement of the objects? Well, there's a couple of ways that we talk about synchronization. Because the product is moving, we want to have square pixels. So we use an encoder that basically determines the width. So, for example, if you have an encoder attached to an object and it's not giving you the correct number of pixels to give you a 1-to-1 ratio, so the fewer number of pulses, you're going to get an image that is basically looks squished, or you're going to basically lose pixels in the vertical. If the part's oversampled, then you will look like a stretch, like you got too many pulses, so now the part's going to look like it's got pulled out. So how do we calculate how many pulses do we need? So let's take the example from last page, and we'll take the pixel size of 0.0014 inches at a speed of 20 inches per second. So the encoded pulse rates, we divide the number of inches per second and how many pixel size, and basically again our encoder should give us a pulse at 13 kilohertz, or 13,654 hertz. If you can achieve this by doing a direct encoder, because it's kind of an odd number, you can also use a wheel attached to a shaft encoder, which then attach to your motion system or your product. So how do we figure out what the size of the wheel is? So again, let's use the example from above, and let's use a encoder that gives us 1,024 pulses per revolution. So in order to get the circumference of the wheel, we take the pulses times the pixel size. So in this case, our wheel circumference to achieve the 0.0014 is 1.5 inch circumferences. In the latest years, nowadays, there are so many programmable encoders out there that you could basically program the encoder to give you the number of pulses you desire per revolution. So that makes things a lot simpler. Next thing you have to worry about too is, which is a lot simpler in line scan, it's the light correction. Here's an example of just a raw image. Basically, we take a line across the, we analyze the intensity across the line, and you can see there's a little bit of a peak in the center, of course, and a drop off towards the end. So cameras, or line scan camera technology, have what they call gain and offset correction. What they do, because again, you're pretty much creating a lookup table, and you're saying, I'm offering you, and I'm going to give you a black object to get the offset, and then I'm going to give you a white object under the lighting that you're going to be using, and you're going to correct for flatness. So after you execute the utilities provided by the camera, you will get a nice flat field correction. That's another terminology for gain and offset. Again, this is very difficult to do in a two-dimensional array, because you would have to do it per pixel basis, both on the X and Y. So here's a utility that was used in applications when you actually have 6 cameras together, and each one of those cameras was flat filled to get the most amount of gain at that, and it's individually programmed. So, and you can tell on the left here there is the line that was used to measure the intensity that's shown on the graph. So traditional line scan applications have been web inspection, because in the past it was very difficult to keep up with the speeds and the kind of resolutions that you needed to do on web material, paper, film, and so on. So what are the defects? You can find holes, dirt, contaminants, rips, things like that. There's always been high speed and also a really wide area to inspect. You're talking about 12 feet, 20 feet, 24 feet conveyors of paper or plastic or film. And you're looking, for objects that are large to small defects. One of the things that you do is you want to classify the defects based on size, range, and also on the type of contracts. For example, if you're looking at, a live material A bright object could be a hole, and a dark object could be a contaminant. And then you characterize this based on, probably 50 to 100 microns, 100 to 200 microns, and so on. In some of the web, there was no really instant rejection because you're either extruding film or you're making paper at high speed. And there's no way you can stop the process because there's a lot of pre-process to the point of when you get to inspect the final product. So what you end up doing is you generate a roll map with a summary that gives you both in the vertical and in horizontal a map of where the defects are. So here's a typical web inspection. So this is a 120-inch web. That's a cross web dimension. And we're doing 350 linear feet per minute. So for us to detect the smallest defect that was allowed, this was a film. We tied up 6 gigi of the 2048 pixels, and we used a backlight. So we're looking for transmission. The 6 lines in cameras go into a vision system, which is basically using a dual quad gigi interfaces, and the throughput of this is 73 million pixels per second. Again, we have a roll, the encoder that clocks the cameras, and then we have a roll trigger that basically gives us a generate of a frame for a 2D frame every 3,560 pixels. Here's an example of again, the user interface where you actually can see a defect. If I can highlight, there's a defect here on the web, and here's what a roll map, but this is a lifetime, real-time roll map, where you have linear footage, okay? And then each camera is divided into a number of lanes, and the pixels or the defects are saved, on the revolution of 1122 on lane 30. Again, when the product gets sent to a converter, they can unwind the product, and take out the defects. Non-traditional line scan applications. We're going to look at 4 different examples. These are applications that we have done with line scans, and we decided to use line scans because of the multiple requirements that we looked at before. So we're going to look at a label inspection, a valve pull inspection, and a medical device. It's actually a metal part of a medical device, in a medical tray inspection. On the label inspection, this is we're scanning a printed label as it was applied to a container or a bottle. We use the OCR to read and compare all the text strings and also some warning labels as well, and there was a barcode. So as the product gets unwind, so here's the label, it gets put into the bottle, then the motion system gives us a trigger, and the camera starts acquiring, and we acquire enough pixels. I believe this was a 1K by 3,500 pixels for the label. So once the whole label is acquired, then we move to the processing. So here's the 2D image on the ramp label. As you can tell, there's a lot of fields. Each one of those fields was given per label to the vision system. So there's things like names, prescription, dates, addresses, and all that. So every label gets scanned and gets inspected to make sure every one of those characters match what the database that was given for that label. The barcodes also checked, and also the warning labels on the right. This process took in the couple hundred milliseconds to acquire and read all those characters. Here's a little bit of the setup. Again, the print hits, and then when the label gets printed, and then the line scan camera with the line light. The next one, we'll look at the valve spool inspection. The problem with this inspection was that there was a lot of surfaces, very small type of defects and a large number of defects on this product. And when you think about this whole round product, the operator, if they have to inspect it by hand, would have to spin it all the way around, look at all the surfaces. So people would say, well, you know, you spinning this product, an operator or a machine has to put it in and spin it and inspect it. With that said, there was a lot faster to do that with a line scan than having a human going all the way around to inspect all the surfaces. So again, we have line scan. We actually had a couple of lights. We had a diffuse light and we had a line light because we actually had to use two sets of lights, and we did 2 revolutions to pick some defects from others. What I'm going to show you is the images that were done with the line light. So here's the spool, or the 2 images of the spool. And as you could tell, they are, if I can highlight that, they are here. There's 1, 2, 3, 4, 5, 6 gaskets. And there's a mesh filter, and there's all these areas that keep the gasket in place and prevent this valve from leaking. There's showing a small crack in here that has to be picked up. Here's a zoom part of it, and where you see the O-ring, and there's a crack on the metal side. So here's the inspection, the part, and what the vision system did is went and scanned the part and did a whole bunch of inspections, again, on all the lands, all the mesh, and all the gaskets, all the O-rings, and it printed out at the bottom for the operator to say, you know, O-ring has some surface defect, which is number 2, and also land number 3, which will be 1, 2, 3, has a crack or chip and failure. Next one, we'll look at a medical device, and we needed to do large magnification on this product, but very repetitive inspection. So because we're looking in a part that's about 3 inches long by about ½ inch wide, we needed to look for multiple defects on the forming. Like you see in this picture right here, you see this small defect in one of the pockets, and there's also, we're looking for some defects inside the pocket as well. So one of the things that, if you think about it, well, why can you do this with a 2D and indexing since you have to move the part? Well, the nice thing about it with a line scan camera is we get a uniform image. So basically it's one long image, which makes the vision tool application a lot easier. Also, again, with the lighting, if you can tell, the lighting is very uniform all the way across. Trying to get that on a 2D, it's quite a bit more difficult. So we use a 2K line scan camera. We use a nice diffuse light, and then the parts get moved onto the camera with a mechanical slide. And again, the camera trigger, we get a start gate when the beginning of the part comes to the field of view, and then we get to the end. And the mechanical slide has an encoder that synchronizes the camera to the motion. So if you look at this, you'll see how the vision tool is running. I took a little bit of screenshots of the vision tool jumping from spot to spot. There is a jump from the screen to screen, but what the vision system does, as you saw, it goes and once it scans the picture, basically it goes in and say, okay, I'll take the same vision tool and inspect this pocket. Once that's done, I go to the next pocket. So it's very easy on the vision application because all you have to do is you change the address of where your region of interest of inspection is versus trying to figure out where they all are. And you find the pocket and then you change it. And all you do is you loop the same inspection with the same setting. And as you can tell here, I found a couple of defects. So I left a couple of red lines. And it also does a contour inspection as well. So if you see the region of interest, there's contour on the ends, there's a contour on the end, and then there's the inspection to find those nice clear areas. So if there's any dark, like in this case, there's some contaminants on the object. So again, when you're trying to inspect, 100, 60, 80, whatever, same objects, it makes it easy because now the image is always consistency. So all you have to do is develop one tool and just put it in a loop, which you increment the address to go to the next location. The next inspection, it was a color line scan. And the reason that we used a color line scan for this medical tray is because there was a lot of color information as well as just intensities. We have to look for rivets and grommets and colors of grommets and colors of brackets and color prints and handles, and a lot of, again, information that could have been detected on a monochrome system, but you also have to detect this to make sure that similar brackets of different colors were put on. This company had manufactured a large number of different types of trays. The nice thing about it is the largest trays was up to 27 inches and the widest was up to 18. So we decided to pick up a two-color 2K front and 3-color line scan camera. So basically we map 20 inches on the horizontal side, and again on the vertical side we had non-limit. They just had a limitation of 27 because what they built, but the system was built to be able to handle longer trays. So we used two 24-inch line lights to cover the whole tray, and again the tray was moved via conveyor. There was a trigger that told the camera when to start acquire as the tray came into the field of view, and the conveyor encoder would synchronize the camera to take the pictures. Here's a picture of the system. So on the right side of the system, that's the output, or where the trays come in. So as you can tell, there's a tray coming in to being scanned. Here's the two white lights, and here's the line scan camera, and then the operator gets a fix. This is the system without any shielding, and then the tray comes at the end and gives the operator a summary of all the things that get inspected. So again, here's all the parts. This tray is actually, there's a lot of failures. One of the nice things it does, it puts red boxes. If you can tell right here, there's a red box, so there's an object missing or a failure. And it also gives you a listing of where all the locations are. Each one of the locations of the bracket, the operators have maps of where they're located. So there's brackets missing, there's handle and a latch, and of course a fail part. So the tray could be reworked and then rerun again. So there's really no necessary throwaway product, just that the customer did not get any incorrect trays. So in summary, line scan offers, pretty high resolutions, things that are nearly impossible to do today with 2D cameras. Just not there. The sensors, at least affordable to the regular consumer. It's easier to illuminate in a lot of cases because you only have to worry about just a stray line of illumination, versus when you have a 2D, you have now a lot more area to try to get consistent illumination. So it is a little more difficult to set up, but once you have it set up, it's a lot more uniform. And again, you have that flat field correction that the cameras offer you. In some of the cases, as you saw, it makes the software development easy, especially when you have very repetitive inspections, because there's a lot of the same objects in the product, like we saw in the medical part, or even in the valve spool. You can move tools around and use the same vision tool over and over and over instead of creating 100 boxes of vision tools. The cost, the starting cost is a little more expensive than 2D. You can do things with smart cameras for the $2,000, where in the vision systems you're starting at $6,000 or $7,000. But if you look in cases where you have to add so many 2D cameras on the extend to see a larger product, it pays off to do that. They're not easy to implement. It's not as easy as you point. You take an image, you light it up, you do inspections. Again, you have to consider your motion, all your product presentation, and you have to have your motion synchronized well with the camera so that you get a correct aspect ratio, especially if you have to do any kind of measurements. And that's all I have for today.
Well, thank you, Fernando, and I want to thank everybody for joining us.